Decomposition reactions typically follow a simple pattern. AB breaks down into its component elements, A and B. So basically, AB decomposes to form A plus B. Here we see that we are starting with one compound and we are ending with two lone elements. This is the exact reverse of a synthesis reaction. Instead of two elements combining to form one new compound, we have one compound breaking down into its elements. The majority of decomposition reactions will always follow this format. One reactant producing two simpler products. Yes, sometimes it gets a little more complicated, but we'll get to that later. For now, the most important thing to know about decomposition reactions is that they are the only type of reaction that begins with a single reactant. No matter how complicated things get on the product side, you know it's a decomposition reaction if there's only one reactant. Alright, here's an example. Lithium chloride, LiCl, decomposes to form pure lithium metal and pure elemental chlorine gas. Don't forget about those diatomics. Chlorine is a diatomic element whenever it is by itself, so we need to add that 2 subscript in order to be correct. See how we followed the pattern? We started with a simple binary compound. That's just a compound that is made of 2 elements. And we broke it down into its 2 elements. One compound decomposed to form 2 separate lone elements. One reactant, 2 products. The same process occurs during the electrolysis of water. When we run an electrical current through water, the water molecules split into hydrogen and oxygen gas. So we see a chemical reaction for the decomposition of water here. That's H2O yields H2 plus O2. Pretty simple so far, right? Well, we wish it was always that easy. The problem with decomposition reactions is that all substances aren't as simple as the binary compounds we were just looking at. Instead, sometimes we have polyatomic ions that are involved, and that's when things get a little messy. No worries, I've got a strategy that will help you every single time. If you go and look at page 4 of your chemistry reference packet, you'll find a section called Guidelines for Predicting the Products of Selected Types of Chemical Reactions. Hey, that might be helpful. Find the decomposition section. Here, you're going to find a list of patterns to follow when decomposition reactions get a little more tricky than those simple binary ones. Type A, the binary compounds, those are the simplest ones, and we've already been talking about how those work. They're easy. Binary compounds always break into their component elements, just like we saw water decompose into hydrogen and oxygen, but they're not always like this. There are some other types of decomposition reactions we need to pay close attention to. For instance, the metal carbonates. Since polyatomic ions like carbonate, that's the CO3 here, since they can't really survive on their own, these more complicated substances can't just decompose into a metal and a polyatomic ion, or here, a metal and a carbonate. Instead, you can see, according to this pattern, metallic carbonates break down into a metal oxide, that's the MO part, and carbon dioxide, CO2. Or there's the metallic chlorates. They follow a similar pattern. Rather than just split apart like binary compounds, these break down into metal chlorides, that's the MCl, and oxygen, O2. And there's the metallic hydroxides. These show up all the time. They're very common, especially in acid-base chemistry, but we'll get to that later in the semester. Metal hydroxide compounds decompose into metal oxides, that's the MO, just like the metallic chlorates did, and they turn into water in the end, so you have MO plus H2O. In all 3 cases, these more complex substances, instead of just breaking apart, they need to break down into smaller, simpler compounds first. Watch out for these 3 special types of decomposition reactions. They're going to show up. Don't let them trip you up. You'll always have these guidelines for predicting the products of chemical reactions, so please use them. We want you to use these tools. So never try to do it on your own. Use the tools we've given you. especially when you come across a decomposition reaction. Make sure you check these guidelines. Determine which type of reaction that you need to follow. Use all the help you can get. All right, see, here they are in action. If, for instance, iron 3 hydroxide, that's this FeOH3, don't forget about your parentheses. If iron 3 hydroxide decomposes, it does not break down into iron and hydroxide. No. Instead, because iron 3 hydroxide is just a more complicated substance, it breaks down into iron 3 oxide, Fe2O3, and water, H2O. Okay, if I just freaked you out because you have no clue where that came from, just let me explain. Here we go. FeOH3, iron 3 hydroxide. It's a metallic hydroxide. Iron is a metal and it's bonded to OH, that's the hydroxide. This is not a simple binary compound that we can just break apart. Instead, we need to go and check our decomposition patterns and find something that matches this reactant. Oh, here it is. FeOH3 looks like this. It's a metallic hydroxide, like the MOH, it's FeOH. The big M represents a metal, and the OH represents a hydroxide ion. That means we need to follow this pattern, the metallic hydroxides pattern, in order to figure out how FeOH3 will decompose. This pattern says that instead of iron and hydroxide, we're going to see this break down into two smaller compounds, a metal oxygen compound and H2O. That's water. Simple. Let's see if we can follow the pattern but substitute in our reactant. Since iron is our metal, we replace the big M with Fe. Following the metal hydroxide pattern, FeOH3 is going to break down into an iron oxygen compound and water. Okay, we already know the formula for water. That's easy. We need to check our charges and formula writing rules, however, to make sure that we write the iron oxygen compound correctly. Since Fe has a charge here of +3, iron 3 hydroxide, and oxygen always has a charge of -2, the correct formula is Fe2O3. If you are unsure about that, you need to go back and review your formula writing rules. Ask your teacher or try this on your own. All right, so our final product of this decomposition is Fe2O3 and our metal oxygen, that's our metal oxygen compound, and H2O, water. Again, all of this is based on the decomposition patterns we found in our chemistry reference packet. Don't try to do this on your own without your reactions guidelines on page 4. All right, let's try another example just to make sure we've got this. If lithium chlorate decomposes, okay, that's LiCO3, we might think it would break into its two parts, lithium metal and chlorate, but that's not true. Don't be fooled by the other simple compounds. This one needs a little more attention. All right, let's try again. LiClO3, lithium chlorate, is decomposing. It's our only reactant, and we know it's going to break down into smaller, more stable substances. We always need to check our decomposition patterns to see which one we need to follow. All right, so which pattern do you think we need to follow here? There it is. This is a metallic chlorate, lithium chlorate. So lithium, Li, is our metal. It replaces the big M, and we follow the pattern. So LiClO3, lithium chlorate, is going to decompose into lithium chloride, that's the MCl, the metal chloride part, and oxygen gas, O2. According to the pattern, we need a metal chloride and oxygen. So that's what we've got here. The correct chemical equation for this decomposition reaction is LiClO3, lithium chlorate, yields LiCl, lithium chloride, and O2, elemental oxygen gas. Don't forget that we also might need to use the metallic carbonates pattern as well. If we ever come across a metallic carbonate compound, if it's decomposing, this is what we're going to use. Out of all 6 of these decomposition patterns, the only 4 you need to be familiar with are A, B, D, and E. Binary compounds, metallic carbonates, metallic hydroxides, and metallic chlorates. Use the patterns. They're here to help you. These are the 4 you need to pay attention to. All right, let's try a real example now, and we've got our decomposition patterns here to help us. Rubidium iodide breaks down. Okay, so what kind of reaction are we dealing with here? Well, we've been told that we're working with rubidium iodide. That's RBI. And we're told that it breaks down. So, this must be a decomposition reaction. The RBI is going to decompose. And by the way, we're also not told about any other reactants. So that means we can assume that this RBI, rubidium iodide, that's the only reactant. And we talked about this earlier. We know the only type of reaction that has only one reactant is, yep, that's it, decomposition. So this is definitely a decomposition reaction. But now we need to figure out what the products are. What kind of decomposition reaction is this? Okay, well, if we go into our decomposition patterns, we might find a couple of clues. Rubidium iodide, RBI, which pattern might that fit into? RBI, I don't see any polyatomic ions, no carbonate, no chlorate, no hydroxide. Oh, this must be one of those simple decomposition reactions. RBI, it's a simple binary compound. It's just going to break apart into its elements. Okay, so rubidium, Rb, and iodine, those are going to be our products. Don't forget that iodine is diatomic. So the correct chemical equation for this decomposition reaction is RBI decomposes to form Rb and I2. How'd that go? Okay, do you want a tougher one? All right, well, here you go. But I think you should try this one on your own first. Pause the video, determine what you think the products will be, and then press play for the answer. Use your decomposition patterns for help. All right, so the first thing you should know about this reaction is that we are given a lot of extra information that could easily distract us. We're told immediately that this is a decomposition reaction, but we're also misled by all this talk of open air and how long the reaction will take, blah, 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 blah. If you know this is a decomposition reaction, don't let yourself get confused by all this extra junk. Move on and focus on predicting those products. Okay, so we're also told that potassium carbonate is our reactant. Remember, decomposition reactions, they only have one reactant. Once we found it, get moving and determine those products. Potassium carbonate has a formula of K2CO3. Before we write anything else, we need to take that formula, potassium carbonate, and we need to figure out which decomposition pattern it's going to follow. This looks like a complicated formula, so we're definitely not dealing with a simple binary compound. Oh, okay, so this is a metallic carbonate. That means we need to use the metallic carbonate pattern. That tells us that we're going to form a metal oxygen compound, MO, that's what that means, and carbon dioxide, CO2. Those are going to be our products. Let's put that into action. Okay, so when K2CO3 decomposes, it breaks down into potassium oxide, that's our MO, K is our M, it's our metal, so K2O, and carbon dioxide, CO2. So our products are K2O, potassium oxide, and carbon dioxide, CO2. This follows the pattern for metallic carbonates because it produces a metal oxide and carbon dioxide. Don't forget to check your charges when you're writing the formula for your metal oxygen compound. CO2, that formula is always going to be the same, but the metal compounds, you've got to make sure you're writing those correctly. Decomposition reactions might seem complicated, but you'll get used to them. If you rely on the guidelines in your predicting products section of your chemistry reference packet, you'll always have the help you need. Just remember, use the patterns. Spend some more time practicing predicting the products of decomposition reactions with the examples I've given you. The answers are available, so you can always check your work.